Welcome everyone from the University of St Andrews. To all our alumni, colleagues and friends from across the globe, thank you for joining us. I'm Tanya Hutt, Head of Development for Science and Medicine, and I'm delighted to be your host for this instalment of our Saints Talk series. This talk's going to last about half an hour and then there'll be a Q&A. And if you'd like to ask a question, please can you type it into your Teams taskbar at any time during the talk, and then I'll ask it at the end. So today we are joined by Professor Richard Bates from the School of Earth and Environmental Science. His talk is entitled Hidden Places, Unlocking the Past Using Geophysics. For the last 30 years, Professor Bates has been using geophysical techniques to unravel the secrets of the past. This interest in archaeology began in parallel with a career that started in the US, working for a geophysics consulting firm. Since then, he and his team have worked everywhere, from iconic World Heritage sites such as Stonehenge to little-known locations all around the world. In 2013, in the east of England, using ultra-high-resolution geophysics, he and his brother discovered hominid footprints after part of a cliff was washed away. Those footprints were 900,000 years old and are the oldest that have ever been found outside Africa. Richard's work has been featured regularly on the BBC, National Geographic, Discovery and the Travel Channels. So welcome, Professor Richard Bates. Thank you for joining us, and over to you.
Yeah, good evening, everybody. An absolute pleasure to be here this evening and talking to you about some of the places I've been and the projects I've worked on in the last 10 to 15 years. I'm not going to go back over a 30-year career here. We certainly haven't got time for that. But I want to give a taster of what geophysics has allowed me to look at and to, I suppose, discover of hidden places, of things in the past, of things that we know less about than we do about things that happened just yesterday or the day before. And I'm going to take us through a walk in time that starts some thousands of years ago and goes back through tens of thousands to hundreds of thousands of years, looking at different sites from Scotland all the way down to ones in Africa. So, you know, hidden places and what is it all about using geophysics? Well, you know, what it's all about here is about how we unlock different places using what's called remote sensing. So remote sensing is a way of looking at the earth, looking at things that are buried in the earth or sometimes on the earth's surface, sometimes underneath water, and getting scientific data about those things, those places. Sometimes they can be, you know, habitation spots. They could be evidence for people living in past or lost landscapes. Sometimes, as I say, they're just in places that are hard to get to, but often they're in places that are actually buried. And, you know, a taster for that there on the left-hand side of the screen is a model of what we think the UK may have looked like some tens of thousands of years ago, and in fact periodically has looked at over the last few million years. And the red being what was actually land in the past, so a very different shape of the continent as we think of the UK and the continent of Europe today. The various symbols on there are different places of interest, and we'll go to some of them. And on the right there you can see one of the places I'm going to visit, which is the iconic landscapes of Lewis at Kalanish. So we're supporting archaeological investigations with geophysics, and there's really four things that I'm particularly interested in. I'm interested in looking at coastlines, at riverbanks, or where rivers were in the past, at vantage points, so places where people would have stood, looked out over landscapes. They might have lived in those places temporarily sometimes on more permanent basis, and also what we would call defensive places within landscapes. And there's a lovely depiction of that from a paper not so long ago about some of these places for some of our hominid ancestors. And on the right there, one of the series of images that were made by a academic called Bryony Coles back in 1998, given us some thinking about this place called Doggerland, the drowned North Sea, and the changes that happened over that over a period of thousands of years. And to take home the message from that series of images there, again, it's these rivers, riverbanks, coastlines, vantage points. So geophysics, well, geophysics involves a lot of toys, or a lot of tools and techniques. Some people call them toys, and they think that I go and have a wonderful time playing with my toys out in the outdoors. Everything from different ways of looking at landscapes, and you can see the range of ways we deploy those sorts of instrumentation here, from very small boats to bigger boats, from walking across landscapes, from flying things in the air. And we are trying to quote here, to see through a glass darkly. Understanding what we can't see with our own eyes becomes very difficult and murky often. And it's not just murky waters we're looking through, but we're often looking into murky pasts. So I'm going to take us through a number of sites to demonstrate this. I'm going to take us going back in time from 5,000, 6,000 years ago, all the way through to about 3.5 million years ago. And we're going to go from iconic places that you'll all recognise, things like Stonehenge at Calanais, through to lesser known places, the Bay of Firth up in the Orkney Isles, over to that footprint site that you heard about in the introduction there on the east coast of England, and then down to an absolutely iconic site in Tanzania, in East Africa there. So landscapes and features. This is a truly internationally recognized feature within a landscape that tells us something about people and what they were doing in the past. But to understand this place, Stonehenge, we've got to understand not just that monument and the immediate vicinity of that monument, but we must understand it in a much broader sense, in the landscape in which it is and set today, in which it was set in the past. We need to extend our knowledge, and our objectives here as scientists is to extend knowledge beyond what is well known, explore the three-dimensional character of what is not easily visible on the land surface. And you can see me there with various instruments walking the fields around Stonehenge, and there I'm using what we call electromagnetic instrumentation to measure the variation in electrical signature and magnetic signature in the ground. That's one form of geophysics. We use LiDAR or laser scanning. We use magnetometry, which looks at magnetic signatures, and we use ground penetrating radar. These are all techniques commonly used and are depicted there, commonly used for investigating the subsurface. And I must stop just here and say that, you know, what I do is certainly never on an individual basis. I'm always working as part of a team, and part of a team of experienced archaeologists. I'm a kind of an interloper when it comes to this. Yes, I've been working on archaeology for 20 plus years, but I'm an archaeological geophysicist rather than a true archaeologist. So let's have a look at that landscape of Stonehenge, and here it is. This is it with a view from above, and you can see Stonehenge at the centre there. And this grayscale pattern has been acquired by laser scanning the surface using drones and aircraft. And all of the little humps and bumps and dots you see on there are features that are evident on the surface, but may not be completely obvious if you walked across that surface. But each one of those is a manifestation, actually, of something that is associated with the past use of the landscape. Here's another view of that, another grayscale view, and this is the magnetic or geomagnetic signature that we've acquired across that landscape. Again, Stonehenge is in the green area. There actually isn't data in Stonehenge. It's the green area in the middle there. And if you know the Stonehenge landscape, you know this cursor is to the north of that. And up on the far northeast is a kind of a circular feature that I'll come back to in a minute, called Durrington Walls, and that's near what we call as Woodhenge up in that part of the world. But again, you'll see on here black and whites as spots of or grey colour changes, and if we zoom in on them, and here's a selection of a zoomed in set of those, you can see various patterns. Now, none of these, if you walked over the ground surface, you would notice. The grass is unmarked where you walk. There's no humps and bumps, but here's a whole range of different grey shaded values that represent changes in magnetic signature. Each of these plots on here is about a 40 by 30 meter a plot of the ground surface. So you can see some of these circular features have diameters that are about 20, 25 odd, maybe 30 meters in diameter. And each one of these represents a previous use of the subsurface. Now, from the geophysics, we don't actually know what that use is, and we have to do more investigation with more geophysics or get into the ground, actually dig it up. And that's one of the major uses of geophysics, is to target where, as an archaeologist, you want to dig. So focusing on some more of these greyish spots, and here's a whole sequence of them, and I highlighted them there in red on the base map. And this sequence of spots in the ground, about 20 meters diameter, have similar signatures, and you can see them form a kind of an arc to the south of Durrington Walls. Durrington Walls on the right hand side there. My mouse goes to there, yeah. So here's Darlington Walls, circular feature, and the red spots on there show us this sort of arc of these dots, if you want, that represent things happening on the surface. Well, actually, you can join them up here, and when we started looking at our data and gathering new data, we see that they're not just an arc of them, but there's actually almost a complete circle of these magnetic spots around Durrington Walls. Now, of course, Durrington Walls is one of the largest features or monumental features in the UK. It's got a large ditch extending in a circular fashion. We know from previous investigations that there was habitation in the middle of this ditch, and certainly Neolithic activities that were going on. So let's have a look at those spots in a little bit more detail here. And what I'm showing on the left-hand side is a series of sections cut through the ground with what we call ground penetrating radar. So each of the spots there you can see on the right-hand side, and each of the left-hand panels is a section through the ground. And I'll just pick out on there for you some of the key, what we call horizons, that show us the nature of those spots in 3 dimensions. So you can see that on the edges of them, there's a sort of a shallow dip down into these, and in the middle is quite a steep dip going down into the base of these features. And in fact, all of the features have similar or uniform shapes to them that I'm showing here. They're all circular, they all have a diameter of about 20 meters, and they all show a depth to the base of about 6 meters. So very, very uniform signatures of features in the ground. I often tell my students that the geophysics is only as good as the ground truth, and so here's actually some ground truth where we've cored and taken samples from the centre of these these pits. And you can see on the right hand side there one of the cores, and you can get your eye into seeing that there is a colour change going from browns on the left, getting gradually paler and paler to a white colour as you get onto the far right core. That's one core, goes down about 6 meters. The base of it goes into chalk, which is the basement rock in this whole part of the world. And the little squiggly lines you can see on graphs on the bottom are geochemical signatures acquired through this this feature. And in fact, not only do the actual features themselves show similarity in property, diameter, depth, etc., across the whole of all of the circles that we see, but also chemically, and if you want, by the core or the geology, this similar each of the pits that we've looked at, suggesting that they've all been perhaps dug in the same way, and suggesting perhaps that they've all been infilled subsequently in the same way. Now, we've got material from here and dated it, and we get a date back at the base of these into the kind of early Neolithic period, which is contemporary with a lot of activity that's going on in Stonehenge landscape generally. And as I say, the chemical data actually analysed for us by a company called Chemostrat, and the dating done by a colleague here in St Andrews, Tim Calanais, has dated all of these. And as I say, we get the same history. So it suggests that something is going on at a particular period in time, something whereby perhaps we would say people have dug these, I'm very crudely sketched here, 6 meter think about that in terms of the house you might be sitting in right now and where 6 meters extends above the second floor windows. 20 meters diameter, that's about perhaps the size of a standard detached house in from one corner to the next. Could they be natural features? Well, here's a sinkhole that's opened up, and you'll see it's got a very different type of shape going conically down to a point at the middle of it. So human constructed or natural? Well, who knows? Interestingly, if we plot them there, and they've all been plotted on a concentric circle around Durrington Walls, and if we in fact look at not necessarily the distance, but the time it would take to walk from Durrington Walls to these features across level ground, which is that arrow, versus across ground that's increasing in elevation, and those going uphill, it's that arrow, versus decreasing in elevation downhill, it's that arrow. Now, speculation is their location is certainly based on a form of measuring distance by pacing. Of course, as you pace uphill, your pace lessens, and you cover less distance. Go downhill, you cover greater distance. So think back to Neolithic, no form of tape measures there, no form of GPS then, but they were probably measuring out things by how many paces it took, or how long, those paces, what the length of those paces were up and down hills. And so, they're certainly purposefully put. We don't know what they're for, but the next stage of our investigation is to go back there and to try and core into some of these in greater detail and find out. So following on that theme, let's go to somewhere closer to home here now, and let's go up to the north of Scotland, and here to the Outer Hebrides, to Lewis, and to the site of Calanais. And here again, we've got iconic stone circles. Again, things which are in a landscape that now today has been buried for most part beneath peat layers. So again, understanding these circular features, we need to dig into them. We need to find out what's underneath to reconstruct that landscape. That's Loch Rogue, and you can see the sites in Kalanish. There's not just one stone circle, but there's a number of stone circles being recognised. And to start off with, I'm going to take you to one, site 11, that sits directly to the north of Kalanish. So there's Kalanish main site. You can see at the end of the line of habitation here. I'm going to go to the north side of this, up onto a hillside, to site 11. And at site 11, there's only one singular standing stone left. However, the peat landscape that you can see these people, volunteers on site, are walking on there, it's been suggested that there are standing stones that are now buried beneath the peat. And in fact, peat started growing about 3,000 years ago, prolifically, as weather changed in this part of the world, and has covered a lot of the sites in this landscape that we're trying to reconstruct. So again, the geophysics is here going to look, hopefully, through the peat and see what we can see. So this is ground conductivity, how electrically conductive the ground is. And what it turns out is that peat is very electrically conductive. It's usually boggy and wet. Water conducts electricity better than dry conditions. And so in here, the yellows and browns are shown with very, very high conductivity, and the pinks and blues with low conductivity. So bedrock here is a Lewisian gneiss, very, very tight rock formation that is of low resistivity values, but the ground itself, where it's got thick peat saturated with water, has high conductivity. The red spot there marks that singular standing stone that you can see in the shot here. Okay, so here we're not actually seeing anything other than mapping the buried thickness of peat. This is another form of looking at that resistivity. And here now, again, the singular standing stone is marked in red there, but you're starting to see more patterns turning up here. Again, it's these sort of spots of black and white. We often show our geophysical signatures as features in a black and white. They show out stronger often than looking at colour diagrams. And you can start to see across the site some other features that we would say, or would suggest targeting for archaeologists to look at. Now, this is the magnetic signature. And again, there's the single standing stone showing out. And on the magnetic signature, you can see lots more of these black-white pairs of magnetic anomaly, as we would call them, that are similar to this one that we've got in this outline for the upstanding stone. So the upstanding stone shows us the signature of a black-white pair, and you can see lots of other black-white pairs across this shot in here. And in fact, if I highlight those, that's kind of how they look. And of course, there's no manifestation of these above the ground, but we think these are buried beneath the ground. And potentially, since they match the signature of that single standing stone that's above the ground, we would postulate that potentially these are buried stone features underneath the ground surface. But of course, I haven't talked, when I've been talking about the features on here, about the most obvious things on this plot, and that's this almost star-shaped or cross-shaped feature of black and white in the middle here, and to a certain extent another one over here. This one absolutely smack bang at the center of what we would postulate could have been the standing stone circle. Let's look at that in a different way. So if I sort of visualize that here and stick these stones back up in a cartoon fashion, then here we go, a magnetic electrical signature right at the center of the stone circle. Nothing there to see on the ground surface. And this sort of a feature is commonly associated with lightning strikes. So what we know is that we've got a very, very large magnetic signature. It can't be in the peat because peat doesn't preserve a signature like this with that wet conductivity. So it must be in the bedrock beneath. In other words, it must have happened before the peat was laid down in this case. And of course, before the peat laid down is when these stone circles were being reconstructed. And of course, to try and get a view for that, and this little reconstruction here of what it might have looked like is one created by Alan Miller's group in Comp Sci here. And again, shows us stone circles. And this stone circle that we are depicting here has a stone at the center of it. Actually, stones at the center of stone circles are quite rare. Of course, the main site at Kalanish has one, and potentially this site here has one. Now, we're not, we will never know until we start digging this place up whether that is actually what this looked like. And of course, why that signature might have preserved itself, or if it is a lightning strike at the center, why it struck the center as opposed to striking anywhere else. Again, we're going to have to dig to find out. So ways of trying to get at the past through these reconstructions, and I'll stop that now. Now, so far we've been all on land, and I want to move us into a different type of landscape here, and the past is a very different place. And I started by saying that we've got a vast area offshore today that would once have been land, and here's a sort of a time scale wrapping showing us the North Sea from about 8,000 years ago to present. And you'll note up north there in that sea level change, and you can see the sea level rise on the bottom right hand side there, that the Orkney Isles were once a lot bigger than they are today, and they shrunk to where they are now. In fact, the timeline across the top here shows us the up and down, warm and cold, or high sea level and low sea level across the last 800,000 years, and we'll come back to that in a minute. We know Orkney for its iconic places such as Skara Brae, Stones of Stennis, Maes Howe, and the Ring of Brodgar, but we might not know offshore what's hidden. And we're going to go into this place here. It's the Bay of Firth. It's quite a long way from this feature here, the Old Man of Hoy, but I put the Old Man of Hoy up there to show you what the bedrock's like across most of Orkney, and that's these flat, almost horizontally bedded Devonian sandstones. So they break off into building size materials very, very nicely, and they are flat layered. And that turns out to be quite good for this landscape and good for the people in the past because it's a great building material. It's not so great for us when we're trying to discover what they've done with that material, because the natural rock breaks into building size chunks and often litters the landscape with building size material that can be misinterpreted as being of human use versus stuff that's just sitting around there from natural erosion. So this is the Bay of Firth, and the top set of figures in there show you changes in sea level going from about 7,500 years ago to about 4,000 years ago as the sea level was rising through that bay. And the bottom image in there shows you what we postulate, what we've reconstructed as a series of sub-basins of what they used to be was freshwater lochs that were inundated by the sea as sea level rose. On the edge or on the banks of one of those lochs, marked with the red star, is a very curious feature. That's shown here on this kind of isometric view looking into the Bay of Firth at one of those previous time periods. And that feature there looks like this on the sea floor. It's about 40 meters in diameter. It's a circular feature. It's very flat on the surface, on the top of it, but it's almost got a rim around it, a rim-like ditch around it. These three geophysical cross sections here show us the flat-lying nature of the rocks at the centre, but show us the steeper dips of the rocks on all of the outside edge of the feature. That's what it's like beneath the surface. And that's a sort of a picture of it on the sea floor. And those 4 X's, I'm going to take us through now what it actually looks like on the sea floor as you go from the centre to the outside. So here at the centre, very much flat-lying slabs. In fact, you might, if you were just shown that picture there, think, oh God, there's beams of wood down there. And in fact, a lot of divers have often thought that about the rock in this part of the world. But they are rocks nonetheless, but they're all flat-lying at the centre. As we start to go towards the outside, there's a little bit of a dip that goes on to these. In other words, they're tipped at a slight angle. And as we get to the very outside, they're almost vertical. But it's not just that they're vertical on the outside, they're bedded so tightly, but also in a concentric fashion. So it's like a ring. It's almost like a ring of upstanding, nearly vertical, tightly packed rocks all around this sort of the annulus of this. Now, what does the rock use look like, or how did they use these types of well-bedded rocks on land? This is the Ness of Brodgar, if any of you have been there. It's a superb example of Neolithic building. They are stacking the rocks absolutely perfectly there on that wall. Beautiful, beautiful architectural and craftsmanship in building. But if you look closely at parts of the site, you will also see rocks bedded at different angles, tightly and nearly vertically oriented. If you visit some of the other iconic sites, for instance, Maze Howe is a ditch around it that's 40 meters diameter. There on the bottom, the Ring of Brodgar has a ditch all around it. And actually, during some of the investigations there on the right-hand side, you can see a very different orientation to the rocks. Rocks that on this landscape in the whole of the Orkneys are generally horizontally bedded. Well, here they're not. They're turned at angles, and those angles are very steeply dipping and concentric to the feature. Are we saying we've got a circular henge, in other words, a ditch feature on the seafloor? Well, certainly if we look at those sea level curves, and here there are our sea level data points, you'll see that this place was flooded, you know, probably 6,000 to 7,000 years ago. Well, 6,000 to 7,000 years ago, there was certainly nobody building the Neolithic features on Orkney at that time period. But what would the people have made about a ring of stones on the sea floor being flooded? That's Woodhenge there, Sea Henge down in Norfolk. I think that's about 4,000 years ago. And that's obviously a ritual memorializing of something that is important to the people there. I mean, this one on the seafloor in the Bay of Firth, it might be natural. There are certain geological phenomena that could cause something like that. We haven't seen anything like that anywhere else in the northeast of Scotland. Or has it been made by humans? Well, more work might tell us. So we mentioned Hayesborough in the introduction, or that was an iconic discovery. So this whole thing of reconstructing pasts to try and figure out more about what's going on was very much the element of what we were trying to do in Hayesborough with my brother. We were trying to find these riverbanks and old shorelines, and here we're very much earlier in time than the Neolithic. In fact, we're going into the late Pleistocene, and in fact middle Pleistocene, down through the upper middle and the lower Paleolithic here. In fact, potentially down to about 900,000 years ago, a time period we know that there are people, if you want, hominids around, because we find cut marks, for instance, on a lot of bone, animal bones that are dredged up in the North Sea. We're finding the tools that they use, these types of tools for defleshing, for breaking things apart. But we've never found any more evidence directly of the people themselves. So again, what we were trying to do here was, you know, narrow this down from a needle in a haystack to a needle in at least a handful of hay. So trying to find the coast, trying to find the riverbanks. Here's my brother, in fact, using the geophysics this time, marching up and down the beach sections and onshore in the fields, trying to make maps of ground conductivity again, because the channels, the old paleo channels, okay, that might have existed back there show up as different conductivities to the surrounding materials in the landscape. And there you can see one coming through. I mark it out in red there. That's one of the old paleo channels that was coming from the land, which is land today, off into the sea, which was sea in the past. And it's the sides of those paleo channels that is very interesting to us. Here they are in cross section, and in fact we're looking here at what we call Pleistocene and Holocene channels, so different ages of channel, and we're trying to get ourselves into the right place in space to be able to sample those channel margins, the channel banks, so places where people might have been active in the past. And we were doing this, in fact, running these resistivity and conductivity lines along this coastline when there was a particularly large storm, actions going on, a lot of erosion, and we had identified that channel that I showed you before as crossing this particular location. And in fact, one of the days we were out confirming that, running our geophysics up here, this had been eroded out of the foreshore. And yes, to the first look, it does look like just a pitted horizon. That's a top-down view of that pitted horizon. But if you zoom in on that a little bit and zoom in again, turn that round this time, there's a characteristic shape to these patterns or pits in the subsurface there. And it turned out this was a surface that was an old channel or river bank margin at a period in the past, a period when people were walking and leaving their imprints across this horizon. Now, we can't date the footprints, but we can date the horizon above and below for features within it. And we can do more than that. We can tell and start to try and understand the group of people. There's a north-south preferential orientation, so that they were arching front to back, indicating a kind of a southward movement as a preferred direction in there. And the foot length stature and this sort of the height length regressions on here gave us an impression, or gave us a set of data that said we had a mixed population of adults and children walking across this landscape. The time period, it put it about between 800 850,000 years ago. And so we've got an indication of the type of people that would have been in this location at that time period. Still haven't got the people themselves, but it's through this sort of targeting that we can get closer and closer and closer to doing that. And so to finish off here, I'll just give you a bit of a step back again, even further into the past, and work we were lucky enough to do this time last year as an absolutely iconic site in the Old Divide Gorge, and this is the human site, or the hominid site, I should say, of Laetoli. So it's over to the west of the Ngorongoro crater. It's often called, you know, the Cradle of Mankind. It's of course where the Leakeys worked for a number of years, and in fact this particular site was where in 1978 Mary Leakey recorded a set of what are now known today as the earliest hominin footprints, dated around 3.66 million years ago. Footprints are preserved here because they're in these soft mud ash beds, again, along lake and river margins. And so that's the trail of these prints, and there was a lot written about them then. And back in 2016, and more recently at 2021, colleagues of ours in the University of Dar es Salaam, Dr. Ichimbilku, had been working on the site to see if there were any more footprints. And in fact, the valley there, or contains a whole range of both animal and human footprints, but since then no more of the tracks other than this one set have been found. So our objective really was to go in and look at the site to see if we can get a better reconstruction of the landscape, find more of those lake and river margins, and potentially for the park authorities there, highlight a strategy to stabilize or to record what's going on. So again, a lot of it's buried, and we have to use a range of geophysical techniques. So there's some students there from the University of Dar es Salaam and actually from St Andrews doing measurements on the site, using drone mapping, using electromagnetics, and using ground penetrating radar to look into the subsurface. So by now, I hope you're getting your eyes into looking at these electromagnetic maps and the colour changes. And here now, really, I'm looking at the colour changes between the pinks and purples and the yellows. The leaky footprint site is shown as this little black square inside the red square on the right-hand side there. It shows up as black today because they covered the site with a plastic membrane I think about 15 years ago now, and covered that membrane with boulders, black boulders. And so they show up very, very clearly on the aerial photography here. Unfortunately, their protection measures have had the actual opposite effect, and condensation on the bottom of them is almost corroded all of the original footprints, so that there's almost nothing of them left. So one of the things that we were trying to do here is not just find the landscape association of them, but find where potentially more of them might exist, so that the park authorities can get in there and potentially preserve them before climate change erodes them. And this whole valley system's been eroded quite rapidly at present. So that's the original site there. And again, you'll see it's quite close to where it goes pinks to yellows on here. There's a site further to the south that, as I say, more recently dug, 3 sets of footprints. And again, they're towards the sides of this pink going to yellow on the ground conductivity maps. Here on that pink to yellow, we've tried to do a cross section through what we believe to be a channel going through there. And on the bottom image on here, that's a 2-dimensional cross section through the earth showing that exact channel. In fact, if we put where we think the footprint horizons are on the base of that in there, then that would be our channel and our channel margins to the south of that and to the north of that, where we actually find those prints. So we've got a set of methodologies now that we can go out and map the whole area to try and find where we think the likelihood of prints are, and they are not. This type of data won't show us the individual prints though, and so we needed a higher resolution methodology, and that's where the ground penetrating radar comes in. So the black square or the black sort of oblong on the left again is where the original footprints were found, and we are doing our measurements all around that in these little blocks, these little squares. And each square actually represents where we've looked in the subsurface like a cube of sediment going down in the subsurface to try and see if we can get better images of where these footprints might be around these sites. If we can get the methodology established, then we can do it elsewhere and do some true discovery of prints. So here's the lower site, Site S, and the known print locations are shown in blue there. And I'll just pick out one of these. I think it's this one, this panel in here, to show you what we've got. And again, hopefully your eyes are getting in. Now, we're not showing individual toe, heel images here now, but we are seeing lines of these spots on this image, and the lines of the spots we are interpreting as potential lines of footprints. In fact, on this is the whole cube of data going from on the top left, the shallowest slice of the ground, and then 5 centimeter slices going down to the deepest on the bottom right in there. So we're sort of slicing through the earth, and in fact, in slicing through the earth, you're slicing through time, you're slicing through geographies and time periods where we think not just people but certainly animals used to move through these landscapes. And so the geophysics has given us a way of looking to find concentrations of these. Yes, it's only as good as the ground truth. We need to dig into there to really find out where, if the technology is working, and hopefully we'll be able to get back there shortly. At this point in time, we've unfortunately run out of the money for going back to this particular site, but we do hope with funding in the future to get back there and to ground truth this, and then to take the work further to look across the whole of the valley, you know, not only for the footprints, but gosh, somewhere out there has to be more than just the footprints. Somewhere out there, as we are looking there and elsewhere, there is more evidence of humans, you know, and that's really what we're trying to get down to. The hominids in this case, humans in more recent time frames. So where are the people? That's what really we're trying to often do here. We're trying to think about that. So paleo landscape reconstruction, we're trying to find out where to look, place the sites within their landscapes, modelling how the landscapes could have been used, and targeting places to look at in detail. Perhaps the dark glass is becoming a little clearer. So thanks, you know, this isn't a sole affair here. It's a lot of people and many more that I've not listed on there. And I hope you've enjoyed that, and I'll be very happy to answer some questions if you have them now.
Thank you very much, Richard. What a tantalising prospect, finding the people. And right, we've got some good questions. If it's okay, I'll just ask you in order that they came in. So sure. Andrew says, you may get onto this, but is GPS, GNSS important to location data? Can you expand a bit on how you use it and relate changes to absolute and traceable location measurements? He says you should be able to get data to locate to less than tens of meters unless you can get around the defence related limitations.
Okay, yeah, it's absolutely vital. It's fundamental to absolutely everything we do, knowing where we're doing it and precisely knowing that. And yes, we do get around the defence things. There's a number of ways of doing that with GNSS systems by putting out what we call base stations. So in fact, both in a marine sense and a land sense, we can get down to centimetres. And so that's what we do on almost every site we work.
Thank you. Okay, so how many sites in sort of percentage terms do you think we know about worldwide? And do you think there are some sites that would change the way we understand history?
Oh, totally. I mean, you know, you just have to look at the news, and sites are being discovered all the time. I mean, I think that you know, we've really looked at a fraction of where, you know, things could have happened in the past. I mean, the offshore areas, you know, the ones that have been flooded. I mean, if you look at the record of sea level over the last 2.5 million years, for instance, there's more time during that period that, for instance, the UK has been joined to the continent than it has been separated. So, you know, there's huge amounts of area that we've just never looked at. Now, that's not to say that there's going to be stuff everywhere, of course, and that's the point about doing remote sensing and doing modeling to try and get down to where specifically to look at. And, you know, will it fundamentally change how we think about people in the past? Probably. Will it fundamentally change how we think and act in the future? Probably not.
Interesting. And on sea level, another question from Andrew, who says, how do you estimate sea levels from 2000 years ago? What uncertainty can you attribute to the measurements, given that it wasn't SI traceable?
Yeah, I mean, it's so figuring out sea levels in the past is a very difficult thing. So what we look for is points in the record with iconic or characteristic signatures of, so for instance, in the Bay of Firth, we've got freshwater lochs, and so the sediment in them is full of freshwater animal and you know, flora and fauna. When the sea comes in and inundates that changes the biology effectively, and so we can see that change in biology and we date that. you know, you can think about things today like we have salt marshes that are in the top of the intertidal zone. So that's kind of, you know, the tide, they sit because of the plant ecology in the communities at the top of that kind of high tide mark. Now, if sea comes in and floods all of that, and that's preserved, we'll know that at that time period that was where the top of the sea was. Or if it, you know, if the sea goes down lower than that, another one forms. So there are a number of different ways we can look at where sea levels are in the past from both the biology and the chemistry of the sediments, if they have been preserved. And our problem often is actually preserving them.
So that goes nicely into a bit of a controversial question from Elizabeth, who says, in an age where climate change is deemed nothing but negative, can there actually be some positives derived from global warming in terms of archaeology and using geophysical research?
Positives from, oh dear, I cannot think of any positive for our global warming and geophysical research. I mean, you know, sea levels will flood further, will flood more things. So we're just going to lose more of that, you know, those types of landscapes. So we're going to make it more difficult. It's more difficult to explore in the marine than it is on land. So, you know, that's certainly not good.
Yeah, so
I'm struggling. I'm really struggling to find a positive.
So on climate change, Roy asks, does climate change actually represent a challenge to the effectiveness of certain types of geophysics, for example, with lower levels of water, longer dry periods, or are there lots of different options to combat those issues?
There are lots of different options in terms of, so actually, you know, water and moisture content in soils, you know, sometimes drier periods can help us. It stresses the crops. I mean, crop marks, you know, we see on aerial photographs in really dry weather. A couple of summers ago, you know, it was a really long dry period and we were seeing crop marks showing up which were representative of buried archaeology, and they were showing up in places we'd never seen them before. So, you know, that I suppose, maybe back to the previous question, maybe that's a benefit of it getting drier. But you know, my argument actually is, and one of the things that I'm quite interested in, we're trying to research is geophysical methodologies that will show us that without waiting for the weather to change, because actually, you know, crop stresses can be told by looking at, for instance, multispectral, if you want, multispectral signatures of crops. And so we can use that and not have to wait for it to dry out. Then, you know, that would be better. So it is sort of an ongoing, quite an interesting sort of field of research at the moment.
Yeah. So on that and the field of research, A. Martin Steffer from Hamburg says, will more universities equip more historic departments, not only archaeology, with geophysics? It seems to give us such valuable instruments.
Yeah, please tell more people that. I'd love it.
Yeah.
Absolutely. Yeah, I mean, it's an expensive game, you know, that's but then, you know, science is expensive. You know, it's a game that marine, it gets, you know, you add an extra 0 or 2 on the end of what you're doing. You know, but we're getting better and better at covering larger areas in finer detail, because computing power is basically going up and becoming cheaper. So in some regards, I mean, you know, what I'm doing today compared to what I did at the beginning of my career, I mean, it's night and day difference in terms of the technologies. Keeping up with those technologies is an issue. Like any science, it's expensive to do that. Yeah.
Yeah. He also says, would you say in the majority of cases you look more for details about existing monuments and sites, or in areas where experts expect that historic monuments may be found? What's the balance?
Yeah, it's probably an equal balance. I mean, you know, your existing sites give us an indication of, you know, that might have been important and that's been preserved in this place. And so it's, you know, there is a perpetuation of sites over time. You know, London is built on sites that go back, you know, 1,000 years or more, because it's an important place. So you sort of, you're doing things in those places. Then there is, you know, it's certainly in the UK, there's things called, you know, development-led archaeology. So like it or not, agree with it or not, the high-speed rail link has gone across countryside that we didn't think, oh, well, we'll go across there because we might find archaeology, but we've had to do archaeology and archaeological investigations because it's going across there. So there's development-led archaeology that lends itself in that way. And then there's modeling. So we've just finished a huge project looking in the North Sea, trying to reconstruct what the North Sea looked like for people in the Mesolithic, and speculating therefore on the models where we should look intrusively, or where how that coincides with things like wind farm development, so that we can then get into there and say, right, let's get data, that could be a good spot, or that our models say that's a place that we need to look at in more detail, so let's look in more detail.
Right, a couple of questions on data interpretation. Firstly, the information is presented is largely images, pinks to yellows. It seems central to the results. How much contention is associated with that interpretation? And also on interpretation, is it all done by humans, or are you beginning to use AI?
Yeah, I mean, just quickly on the latter point, AI, yes, it is absolutely coming in now, and it's being looked at as it is with most scientific fields. There's, yes, I showed you a whole range of nice color plots because they're easier to see and sort of talk about for anybody to get their eye into thinking about what and how to interpret. We go from that to then starting to plot the statistics of, ranges of values and associations with ground truth. So, once you've got the ground truth, and again, it's only geophysics is a bunch of numbers and is only as good as the ground truth that you've got to compare on a particular site, on lots of sites, or on a global data set. And we would then start to employ, look at that statistically to say the likelihood of our interpretation being X or Y based on a kind of a numerical analysis, beyond getting your eye in and squinting and sort of saying, oh, that colour looks nice. But as a first pass, you're out in the field, collect data, and we produce those kind of maps to say whether we're in the right ballpark or not, or it's a bust or it's not a bust, or that it's worth carrying on with the data collection. Yeah.
Right, some questions now about the actual sites. Jeff says, what is the evidence that Darlington Pits is anything more than a flint mining shaft?
Yeah, so flint mining shaft, that's a good one, and we certainly have flint mining shafts in the area, and they do show sort of similar signatures near the surface. The trouble with them is that we've always had a shaft going down much deeper beneath the base of that kind of 6-meter pit, and what we've not found in any of these so far is those continuation shafts going deeper. They all seem to stop at about this 6-meter level, sort of flatten off on the base and don't extend beyond that. So 1, 2, yeah, maybe if we did find that, and on top of that, why dig them in a big old circle around another monumental feature? I mean, you could make the argument certainly that the whole process of mining flint has a ritualistic sense to it, so maybe that's enough of a reason to put them in a concentric circle like that. Ultimately, I suppose you could never say until we dug one out entirely that we could prove it one way or the other. We don't also see any debitage from it, so we're not actually seeing, one would imagine, kind of a mixed up sequence of material that have been pulled up mainly from the chalk to be filling them in, whereas the fill isn't like that. It's more complex and yet more consistent through all of them. So a whole range of things would, tends us to think that they're not mining pits.
Thanks. How did the footprints in the riverbeds survive?
Yeah, I mean, this is absolutely. So how do such ephemeral things ever survive in nature? And certainly they're not the only footprints that have survived. We can go around the coast of the UK and look at Bronze Age, Mesolithic footprints in the Severn Estuary. We've got Bronze Age all the way up the Welsh coastline. So how do footprints survive? And it would seem, when you think about it from a geological perspective, you go and squelch on the mud, and we all know if we go down to the beach today, or with an estuary, squelch in it, the next tide comes in and it's gone. It's been eroded away. It does rely on a specific singular event that comes in and perhaps puts a layer of sand on top of it. It puts certainly a different material on top of that footprint layer, and subsequent to that, that material that goes on top is not eroded. Now that is, you would say, God, what's the chance of that happening? And it does seem really unlikely. And yet, all throughout space and time, we see this happen. It's the, for those footprints to preserve at that place is, of low likelihood. And so there must have been loads more over all the time period that people were walking there, over maybe, generations, maybe hundreds, maybe thousands of years. Who knows? The fact that one set is preserved seems really unlikely, and yet they are preserved just by that quirk of an environmental signature changing. And this happens all around the world, and it's just a quirk of something that you're lucky that's been preserved at that particular point in time, one particular point of events, and amazingly it's not been eroded ever since.
Lucky for us.
Yes.
A question on lightning. Does it tell us whether Roy asked, does it tell us whether the strike or the circle came first? And can you explain the geophysics signature of the lightning strike at I can't remember how to pronounce it. Calanais.
Yeah.
Why does it still show up?
Yeah, so when lightning hits something, hits a material, if it hits a church steeple and you don't have a lightning conductor down the steeple, it can effectively, the discharge of that lightning into that material, particularly when it's a very resistive material, so it's not conductive, so it can't conduct that energy, if you want, away, it can't conduct that signature away, then it'll break, or it sets itself up with that signature. Now the magnetics comes in because of that discharge of it's the electromagnetic component of that sets itself up, but it must be very resistive conditions. So if it hits something that's wet, and this is why we don't see lightning strikes like everywhere in the landscape around us. You get a lightning storm come across the Fife here, and it'll hit fields, it'll hit things, and it dissipates away because of two reasons. One, because it's wet, the ground is generally wet, and it conducts that signature away. And of course, in many places, it's ploughed out. It's just that signature, if it does set it up, the magnetic component sets up in the soils, then the next ploughing just churns it all up and it turns away. So the places we go to look for similar effects are dry areas like deserts, and you go to deserts around the world and you'll see these lightning strikes there. So we know that if it struck, it must have struck dry material, so the peat couldn't have been there, and the bedrock here in Lewis is what we call Lewisian gneiss, which is got a very, very low resistivity. It's very tight rock, it's dry, if you want to use that term. So it must have been a huge signature that hit that and has been preserved in it, because it's bedrock it's been preserved in. So subsequently, the peat has grown over it, and it's kind of locked in the rock, and that's it. At the centre of a stone circle, what came first? Well, we don't know. I mean, even if we dug that site up, would we ever know? Don't know. The fact it struck at the absolute centre of the stone circle, you could say there's two things. Either there was something at that centre of the stone circle that maybe a major stone that it struck, and that's been shattered, and if we dug the site we might see that, or it struck that place and the people somehow noted that, and they wanted to memorialize that, and they put the stone circle around it. Now we don't know in this particular case either one which might have happened. If we go and look at sort of recognition of lightning strikes in the archaeological record, we can go to places. So in Southern California desert, there's a classic set of lightning strikes that have hit a set of boulders, and the people there recorded that particular the event by petroglyphs of what looks like lightning. There's a site in Armenia, Karahunj, which is a stone circle, and there, each of the rocks that has been struck by lightning has now a human bored hole through the middle of it. So they've somehow noted that, and they've marked those stones in a particular way. I think the whole thing of the marking of lightning within the archaeological historical record and what it means to people, I don't know of anybody who's ever researched it. I mean, it's a fascinating subject. I've got probably half a dozen places around the world where I know that our ancient peoples have noted these sorts of things and thought about it, but that nobody's researched it. I mean, there is, when I can get around to writing the research proposal, I think it's the next thing I'd love to do. I mean, I think it's fascinating, and I don't know the answer.
Oh, well, we've run out of time. We've had some absolutely wonderful questions tonight. I'm
Yes.
very sorry if we didn't get to yours, but I want to thank you, Richard, so much for doing this talk. Thank everybody so much for being here. Join us next time on the 13th of December, where we've got a talk by Professor Laura Moretti from the School of Art History. Thank you, everyone, and goodbye.
Thank you.